What's up, peeps? Yeah, I'm out again. Just for the morning. I'll be back this afternoon. I'll be after school if you need help with any of this. But it seems like you're doing pretty well. So, yeah. This is a sort of really the last part of this unit, and we're dealing with a special kind of problem, a special kind of situation where an object is thrown straight up and it comes straight back down. Um, yeah, okay, sure. And I'm going to give you this initial condition that it's thrown upward at 49 meters per second. Now, just for this slide, let's assume that g is just 9.8 meters per second squared. We're going to drop the 1. It's just going to save us a little bit of what's that word? I don't know. A little bit of a pain in the butt. So, question 1. Let's figure out how long it takes to get to the top. All right. Well, here's things we know. V initial, 49 meters per second upward. A is G is 9.8 meters per second squared downward. We want to know what V. No, we want to know what T is. T equals question mark. How long does it take to get to the top? Well, they have just told us a given. When the object gets to the top, what happens? Just scream it. Just scream it out loud. Go ahead. No, I'm going to try this. Bree, what happens when it gets to the top? Bree, you have to answer. Go. I can't hear you, Bree. What happens when it gets to the top? Yes, exactly. It stops for 1 instant. For 1 instant, its velocity is 0. Nice job, Bree. So we can say that at the top, we're not saying that the object actually stops there, and sits there, or that's the end of its motion. But if we choose to make that the end of our analysis, we can choose that instant to be our final instant. And therefore, our final velocity is 0. Okay, now let's find an equation that has these 4 things in it. Ready, go. Yeah, equation Vf is Vi plus AT. And so that means that T is Vf minus Vi over A. Or substitution, T is 0 minus... Oh, what I didn't do yet is I didn't choose my positive direction, right? Let's say that positive is upward. That makes this positive, makes that negative. All right, now we can do our substitution. So Vi is positive, so 0 minus 49 meters per second divided by negative 9.8 meters per second squared. Notice that our 2 negatives here make this amount of time a positive 5 seconds, exactly 5 seconds. Okay, there's our time in the air. Okay, so let's say now that this object is fired upward. It takes 5 seconds to get up to the top, and then it comes back downward. What we want to do here is, like it says, estimate its position. Sorry for this. Estimate its position at 1 second intervals and calculate its speed at those intervals. So we know for sure that it takes 5 seconds to get to the top. Does that come up next? No. Good. 5 seconds to get to the top. So the question is, so here's, this is T is 5 seconds. All right? So its position at these 1 second intervals. Well, it could work like this, right? 1, don't draw this, 2, 3, 4. Those are pretty even intervals of distance. So what do you think? Make sense that it goes the same amount of distance in each second? What do you think, Zoe? I know, this isn't going to work. So, yeah, it's not going to work that way, right? Because, of course, this object slows down as it goes upward. So what's going to happen is we're going to have larger intervals at the beginning. So maybe like, yeah, I don't know. Maybe like it goes to here and then a little less and then a little less, and then that's 1, 2, 3, 4, 5, something like that, where the distances, that's not very good, is it? The distances between those positions get smaller and smaller as time goes on, okay? Well, so let's say it works maybe something like this. Something tells me that that's actually like the math. I tried to make this mathematically accurate. We can talk about that if you want. If you remind me on Thursday, I'll tell you how the real mathematical way works. But that's pretty darn close. Okay, so it does something like that. All right, let's do a little calculation, or maybe just a little thinking, and figure out what its speed is at these 1 second intervals. Well, here's one way we can do it. Right? We could say that, okay, VI is 49, upward. A is G is 9.8, downward. VF is question mark, and let's just do time as 1 second. All right, now again, if we say that upward is positive, this is positive, this is negative. So if we do VF is VI plus AT, well, that's VF is, 49 plus negative 9.8 times 1 second. Well, notice that's 49 meters per second plus negative 9.8, or minus 9.8. So that gives us at our first second, let me move this out of the way just so you can write that down if you need to. Right, we're just calculating, using one of our kinematics equations, how we find the speed after 1 second. Big deal, this acceleration has to be negative. So what we end up with is, at 1 second, there's our speed, 39.2 meters per second upward. Now, what you might notice also is what we just did here was to go from 49 to 39.2, you subtract 9.8 meters per second, right? Because what does G mean? If G is 9.8 meters per second, it means that velocity changes by, it changes by 9.8 meters per second every second. So after another second, it's going to change by the same amount. So if we just literally subtract another 9.8 meters per second, we get 29.4 meters per second. So I'll write that, minus 9.8 meters per second. Not squared. Right? I'm not talking about what the acceleration is right here. I'm talking about how much the velocity changes. It changes by that much in a second. It changes by that much in a second. In the next second, it changes by that much again. I'm just subtracting 9.8 meters per second every time. Just going to move this. You'll still have it written, of course. We subtract another 9.8. Oh, look at that. Coincidence? No, not a coincidence. I chose the initial velocity carefully because after one more second, when it does take 5 seconds to get to the top, oh yeah, at the top, that's exactly what we said, right? We said that the velocity for an instant at the top is 0. Okay? Yes, minus 9.8. Yes, minus 9.8. Yes, minus 9.8. Now, bear with me. Listen to this. Remember this equation? Of course you do. It's D equals V average times T. Remember that? Yep, I remember that. Now, that says that from here to here, this distance depends on the average speed over that 1 second. Right? Well, the average speed is, remember, take one speed, add the other, divide by 2, like finding the average of 2 test scores. So take 9.8 plus 0, well, that's 9.8, divide by 2, that's 4.9. Trust me, 4.9 meters per second for 1 second. The 1 second it took to go from here to here. That means that that distance, this vertical distance, in the final second is literally 4.9 meters. Yeah? Okay. Now, in the next second, from time 5 seconds to time 6 seconds, well, what happens to velocity? It changes by the same 9.8 meters per second, still downward. So what we get is after 6 seconds, its speed is now 9.8 meters per second downward. And notice, our average speed from time 5 to time 6 is the same, well, average of 0 and 9.8. That average is 4.9 meters per second. It's the same time, 1 second. And therefore, we fall the same exact distance downward in that next second. So this is another, the same exact 4.9 meters. All right, I just want to show you why I drew that dot exactly straight across, this dot here. Why did I draw this exactly straight across from that one? All right, because it literally falls the same exact distance in that second, in this second from 5 to 6, the same distance it went upward from second 4 to 5. And the same pattern happens, right? As we keep going here, well, at time 7 seconds, and 8, and 9, and here at 10 at the bottom, we'll be at the same exact position we were going up, but now we're going down, all right? And the speeds are the same exact speeds they were on the way up as they are on the way down. The only difference is the direction of them all has changed. Why don't we pause right now on our YouTube and let you write down anything you haven't written down. Ready, pause. Now, the one thing that I want to mention for sure is that we're not, I know this looks like I'm taking an object and throwing it like across a room, like from left to right. It's really what we're trying to get at is something that we literally throw straight up and come straight back down. But if I drew that diagram, it would be hard to label lots of different times on it. So this is not really supposed to look like a two-dimensional arcing path. I'm just sort of almost stretching out the drawing in time. All right, so just pretend, just assume that this really talks about something that goes straight up and comes straight back down. Okay? Now, what I'd like you to do on the next page, just soak this in. Just soak it right in. Get a look at it. Just all the glory of it all. Very good. You can refer to it as you need to. What you're going to do is spend, let's say, 5 minutes, maybe 4 minutes. Yeah, let's go 4 minutes. Maybe 3 minutes. Yeah, probably 3 is probably good. There's only 4 questions. I want you to fill in these questions. All right, so we'll pause. Mr. or Miss or Mrs. Substitute, thank you very much. Press pause, and we'll be back in 3 minutes. 3 minutes, ready to go. Okay, now that we're back, we're going to fill these bad boys in. All right, question 1. How does the final velocity of the ball, just before it hits the ground, of course, compare to its initial velocity? Well, notice that VI was 49 meters per second upward. VF, 49 meters per second downward. So there's a 3-word phrase we use for these. What's that 3-word phrase? Mr. Kiesel, 3-word phrase? I know you're not a very noisy kid, but just go ahead, Kiesel. Say it. 3 words about those 2 velocities. Yes, exactly. They are equal and opposite. Great physics, I don't know, physics principle? I don't know. It happens a lot in physics that quantities, physical quantities happen to be equal and opposite. Probably in lots of science. Now, a simple formula or equation that summarizes, well, really that summarizes this, or what's true about VI and VF. Anyone come up with that equation? What about you, Rachel Signore? This is ridiculous, asking questions like this. Well, here's what I would say. Really, if we say that VI is 49 and VF, well, by downward we can say negative 49. Well, we can generalize and say that the final velocity is always equal to the initial and opposite, right? There's a nice little equal and opposite equation. VF is negative VI. I hear you, some of you saying, I have VI as negative VF. Well, that's the same thing, all right? What's nice about this, right, is if we say, okay, VI is 49 meters per second. Well, VF is negative 49 meters per second, right? But that works. Okay, number 3, total time the ball is in the air. How does that compare to the time it takes to get to the top of its path? Well, if you notice, T total, time in the air was 10 seconds. T up was 5 seconds. So in general, how does the total time that an object spends in the air compare to the amount of time it takes to go up or come down? Well, I'll do this. We'll say that T total is, well, twice the time it takes to go up and twice the time it takes to go downward. Those are T's. Stupid. There you go. Okay? So, of the total time the thing spends in the air, it spends exactly half going up and exactly half going down. Now, here's a big deal, what I have to make sure we're okay with. This assumes launch position equals landing position. Real important. It assumes it's caught at exactly the same height it was thrown from. Sorry, I had to get water. So, oh yeah, there's our in general. Now, what do we call this? I don't know if people really, if people really call it this or not, but I call it symmetry of motion. I think there's 2 M's. That's what I call it. And we're going to apply a couple of these symmetry of motion principles in a couple of problems. Ready, set, go. Now here's some some tips for solving problems. You know, big deal is that you have 3 options about of how to approach these things. Okay? You have 3 options. You can say, okay, let's say that it actually starts here at a speed VI going up, right? And then, well, if we say I'm going to start analyzing at the instant it's launched, I'm not going to stop analyzing until the instant just before it lands, right? Well, we can say, all right, then our V final is equal to the negative of the opposite of our, V initial. We know that A is G the whole time, 9.81 meters per second squared downward. And that's kind of what we know. All right. Well, I could do this too. I can say here time is 0. Here time is what we call, I'm going to call it capital T. It takes some amount of time, capital T, to get to the bottom. All right. Now, there might be some questions where it's in our interest to only look at half the flight, right? Maybe I want to say, okay, it's thrown upward with a speed V initial. But for some reason, for whatever reason, I don't care what happens after it gets to the top. I want to use that as the final part of the final instant in my analysis. So what we do here is we could choose this and say, okay, let's choose VF as 0. Even though we're not saying the motion ends there, as far as our analysis is concerned, we can say, let's just stop analyzing there. Again, A is G is 9.81 meters per second squared downward. Now, I would say that if T is 0 here, check out my notation. Well, we said it spent a total amount of time, capital T, in the air. We're going to say that's half that time, right? Now, there are other times, problems, situations, in which it might be in your interest to say, I don't care what happened on the way up. I'm not going to start analyzing until it gets to the top. When it gets to the top, I'll start my analysis there. That's going to say the initial velocity is 0. Now, you're not going to know what VF here is at the bottom necessarily, but it's not necessarily a given. All right, but it would have some, VF going downward there. Again, right, A is still G, is 9.81 meters per second squared downward. And if we called time t0 here, the time at the bottom would be, like we said before, half that total time. Well, how do you know which one of these options to use? It really depends on, like it says, it says somewhere, I feel like, maybe not. It depends on what the question asks, really. It depends on what you know and what the question asks. Okay, so we're going to look at a couple of situations that deal with these. So here's one where we have a rock thrown straight in the air. How long does it spend in the air? All right, well, how long does it spend in the air? Well, what that sort of says to me is we're talking about the entire flight, right? I'm going to write that, entire flight. All right, so what that says to me is, let's look at this whole thing. It goes up, it comes back down, right? Now this says that it's thrown up with a velocity of 22 meters per second. Well, boom, right off the bat, we are told the value of something else, especially if we're looking at entire flight. We know that when it gets here, boom, back to the original launch height, VF is 22 meters per second down. I'm even going to write these, VI, 22 meters per second. VF, 22 meters per second. A is 9.81 meters per second squared down. We want to know what T is. How long does it spend in the air? Well, let's not forget, we should always do this. Again, if you want to make positive downward, be my guest. Upward, positive. Downward, negative. Downward, negative. What equation has those four things in it? Of course, VF, VI, AT, GT really, but A is fine. So VF, VI, AT, VF, VI, A equals T. So that's negative 22 minus 22 over negative 9.81. So that's about, I believe, 4.5 seconds in the air. Okay? What do you think? Pretty straightforward? Check this out. I'll show you a trick. Another way to solve these, if you dig this. In the beginning, it starts here. In the end, it ends there. Same place. So I'll call this method 1. Here's method 2. This is just kind of neat to show you that it works out the same way. The big deal, you know what the total displacement is? Go ahead, yell it. Yep, 0. Now we can still say that VI is 22 meters per second upward, right? A is still 9.81 meters per second downward. Let's keep the same sign convention. We'll make that negative. D is 0, and we want T. Well, what equation has those four things in it? Well, of course, VIT plus 1/2 AT squared. Well, D is 0 because it comes back to the place it was launched from. We get, let's see, I'm going to say that negative VIT equals, 1/2 AT squared. Well, we can divide both sides by T and get that T is negative 2 times VI divided by A. Well, check this out. Right here, whether or not you recognize it, we have the same exact expression. Because remember, what's VF in general for one of these symmetrical things? We said that VF is negative VI, right? Oh yes, this is negative VI minus VI. Well, that's negative 2 VI. We get the same exact method, or the same exact, I don't know, conclusion out of two different methods. I like, you know, I think it's pretty. Okay, so 4.5 seconds, fair enough? Excellent. Why don't we pause right now? You can write down anything you haven't written down yet. Start up again in a minute or so. Okay, so next problem. Arrow shot straight up in the air. It lands 6.5 seconds later. What's the maximum height it reaches? You'll see a lot of these maximum height questions. All right? And I hope this leads you to the idea that I can't look at the whole path, you know, from beginning to land, here to here, because, well, it doesn't tell us about the top. We want to know how high it goes. So that means we either have to do the first half bottom up or the second half top down. All right, so we have those two options, on the way up or on the way down. Well, let's see. If we do on the way up, we would have VI is unknown. We'd have VF is 0. We would know that our A is G. And we do know that our time is how long? Not 6.5 seconds. Yeah, 3.25 seconds. Right? Half the time. And we're looking for D. Well, I guess the question becomes, is there an equation with those four things in it? Well, the answer is no. However, if we do this and say, well, if we go top down, we can say that VI is 0. We can say that A is G. We can say that, well, we don't know what VF is, but we do know the time, 3.25 seconds, and we want to know D. Well, the question now is there an equation with these four things in it? Well, the answer is yes. If we say that D is VIT plus 1/2 GT squared, it's okay to put G right in that equation. Right? There's the four things we either know or are looking for. All right? What's also nice about this, right? VI is 0. That entire term goes away. And we're looking for D. Right? So let's just make sure we do this. Let's say that positive is up, right? Well, we're going to get that D is 1/2 times negative 9.81 meters per second squared times 3.25 seconds squared. Remember, we only square the time. It's not parentheses 1/2 GT squared. It's just 1/2 GT squared. So let's see, 3.25. You should all have a calculator out, by the way, if you don't already. Yeah, so I get, well, you get D is negative 51.8 meters. Why is D negative? Because this really means that D is 51.8 meters downward, right? If upward is positive, well, then negative means downward. Well, what it means is, you know, of course, going from the top to the bottom, because this is the, you know, method we chose to analyze this. Yeah, it went 51.8 meters downward. So what's the maximum height that the arrow reached? Well, the maximum height was 51.8 meters, right? Boom, there's your answer. We wouldn't want to leave that as negative, right? You want to be careful about the answer here. You know, just make sure you're answering the question. Okay? Example 3. Um, I think, wait, hang on. Yep, good. This one, I'm going to ask you to do. You do. But the answer is 12 seconds. Now you're going to get 6 seconds. You're going to be like, what? Oh, I get it. So just be careful. All right, so do that one. I'm also leaving some other stuff for you to do. Hopefully it's some more of these questions. I think it is. And when you come in tomorrow, we're going to have a quiz. Yeah, that's right, a quiz. And that quiz is going to be not on these symmetry of motion problems, but on plain old free fall problems I mean, these are free fall problems, right? They're just a special kind of free fall problem. They're going to be on free fall problems and on regular old, what I call kinematics problems. Any old problem where you use those big, ugly equations. All right, you don't always have to have acceleration equal g, right? You know, we had what do we have? We had a cart going down that track, and acceleration was maybe like 28 centimeters per second or something like that, right? So not all accelerations are g, but we can solve all problems involving acceleration with the big ugly equations, the kinematics equations. Okay, so we'll have a quiz on that on Thursday. All right? All right. See you tomorrow.